Good morning, students. My name is CHSV Prasad Rao. I am working as senior lecturer in electrical department and working at Government Polytechnic, Yadgirigutta. We will continue with lesson AC motors. In that, we have going with the synchronous motor. That is first chapter 1, synchronous motor. In this synchronous motor, last class we covered V and inverted V curves of synchronous motor. V and inverted V curves. So, on which parameters the V and inverted V curves are drawn? Anyone can guess? On which parameters we have drawn the V and inverted V curves? We have anyone guess? If you draw the curve between armature current and you have to take the x-axis and y-axis. We have to draw on the x-axis we have to put the excitation. On y-axis we have to put the power factor. Power factor. So if the curve is drawn between excitation, that is field current, and power factor, then it is inverted V. If we draw the curve between armature current and excitation, then it is V curve. There are two curves. One is with on x-axis, uh, we have to take the excitation, that is field current IF. On y-axis, we have to take armature current. And if you draw the, and by keeping the load as constant, a particular load, that is, suppose at no load, keep the load as no load and vary the excitation IF and note down the values of armature current. And if we draw the curve between armature current and excitation, then we can get a V curve. So again, you change the load, that is, put it off load or 1/4 load, and again vary the excitation and note out the armature current. And if you draw the curve between armature current and field excitation, then we can get another V curve, which is at 1/4 load or off load. So that means by keeping the load as constant, we can draw the curve. So at the same time, if you take the power factor also, and if you draw the curve between power field current IF and power factor, then we can get inverted V curves. In this case also, same thing. We have to take the field current IF on the x-axis and power factor on the y-axis, and you keep the motor at some particular load. Suppose if you kept on no load and if you change the excitation gradually and take the readings of power factor, and if you draw the curve between these two, field current and power factor, then you can get inverted V curve. Again you change the load, put some particular value, again it constant, that is half load or 1/4 load. Again vary the excitation and take the reading of excitation and power factor. And if you draw the curve between and if you draw the curve field current and power factor, then you can get a inverted V curves at different loads. So so in these two currents, the V and inverted V curves. So in inverted V curves, the inverted V curves, we have noted that at the peak level, that is called the UPF, normal excitation, which is at maximum value. So left hand side, we can say lagging power factor, and on right hand side we can say leading power factor. So in inverted V curve, the maximum peak value is called UPF, and left hand side lagging and right hand side leading. Similarly, for a V curve, V curve is drawn between armature current and excitation. In the last class, as we studied the effect of excitation on armature current and field current, that is at three conditions: normal excitation, over excitation, and under excitation. So from these, what we noted, effect of excitation. So if you reduce the excitation, if you reduce the excitation below the normal, then EB is less than V, and it is drawing lagging power factor, but current is high. Again, under over excitation, in over excitation, what happened? Excitation is greater than normal, then EB is greater than V. Then what happened? The power factor is leading and current is high. So in both lagging and leading, the current is high. The current is high. So at unity power factor, the current is minimum. So V curve, which is drawn between field excitation and armature current. So in V curve, the bottom line, that is at the middle, it has the bottom line, that is called the minimum armature current when it occurs when the power factor is unity. So from this curve it shows at unity power factor the armature current is minimum. In both lagging and leading, the armature current is high. And what about the power factors? It is lagging and it is leading. Only at the middle it is unity power factor. So as we discussed in the last class, armature current is minimum at unity power factor. So for excitation higher than normal, the magnitude of armature current will increase and the power factor is leading. At excitation lower than normal, the magnitude of armature current again increase, but power factor is leading. So the shape of the armature current I versus excitation is similar to a letter V. In English alphabet E. This is the characteristics of the motor, which is in the form of a English alphabet V, which V is the characteristics which is drawn between armature current IA and field excitation IF. So a series of V curves can be obtained if the load on the motor is changed. That is no load, off load, 3/4 load and full load. So and keeping the load as at particular load as constant and changing the excitation, then we can get the then we can able to draw the curves. So you suppose if when the excitation is changed at a particular load, the armature current and power factor also varies. The characteristics if you drawn between power factor and excitation field current, then it is inverted V curves. Since on overexcited synchronous motor draws leading power factor current and and its behavior is similar to a condenser and is therefore called synchronous capacitor or synchronous condenser. So that explains the details about V and inverted V curves. So today we will today we will check synchronous motor used for power factor improvement. That means how we can it is used to improve the power factor. As I told, synchronous motor overexcited under no load. It draws leading power factor. And we will do the problems on synchronous condenser also. So synchronous condenser. So a condenser or capacitance always draws leading current from the supply. So we know the synchronous motor can be operated at unity power factor, lagging power factor and leading power factor just by changing the excitation. So the ability of synchronous motor to operate at a leading power factor when overexcited is utilized to improve the power factor of the system. As I told in the previous class, all industries has to maintain the standard of the power factor that is 0.85. They will design electricity board, they will design as a 0.85 or zero point 0.9. Whereas if you see the industry, they have all are induction motors. Then what happened? All the motors draws lagging current. So what happened? The overall power factor of the plant is reduces. To improve it, what we have to do? We have to connect synchronous motor with over excitation in parallel with the bus bar to improve the power factor. So that's why we can use the synchronous motor with over excitation as synchronous condenser and to improve the power factor. So when a synchronous motor is used for power factor improvement with no mechanical load, then it is called synchronous condenser. So it draws a leading current, hence the name is synchronous condenser. It is used where power factor is low. So at no load, we can neglect the losses. So synchronous motor operate at alpha is equal to 0, that is load angle or coupling angle is equal to 0. This gives supply voltage and back EMF EB are out of phase. So if you draw the leading power factor, that is zero power factor leading vector diagram where EB is greater than V, then it is like this, where armature current IA is equal as EB is greater than V. So armature current IA is equal to EB minus V by XS. So that is over excited. And armature current leads the supply voltage. Suppose the excitation is reduced, then it can say lagging power factor where EB is less than V. See here, if the armature current is changed, that is V minus EB by XS. Since EB is less than V, so armature current IA lags the applied voltage. So this is the figure how it is showing as the plant, and they have all induction motor. It draws lagging power factor kVA, and induction motor takes lagging kVAR from the supply. Hence it operates at lagging power factor. Then what happens? It results in poor operation. It results in poor operation. Suppose for this induction motor, if you connect a synchronous condenser in parallel with the bus bar as shown in figure, then what happens? Then it reduces the kVR and kVA from the supply as the synchronous motor is operating at a leading power factor. Then what happen? The overall power plant power factor, that is including both synchronous and induction motor, is increased when we connect a synchronous motor in parallel with the bus bar. So a synchronous a overexcited synchronous motor is connected in parallel with the induction motor, and it supplies lagging KVR only. So distribution lines are relieved of completely supply the lagging KVR needed by the induction motor. Then what happens? The power factor automatically improves. The supply lines have reduced KVA and reduced current. So then what happened? The overall voltage regulation and the line losses, the voltage regulation of the line increases, the line losses reduces. When line losses reduces, automatically the efficiency will be increases. So induction motor still operates at a lagging power factor, but with the same kVAR and kW rating. So it is the combined load consists of overexcited synchronous motor and induction motor will work at improved power factor. So if the lagging kVAR demand demand required by the induction motor is completely met by the overexcited synchronous motor, then the combined load operates at unity power factor. That is, the power factor is improved. So if you draw the vector diagram where OA OA is load kVA is load OA, that is load kVA, sorry, OA, that is load kW, and OB, this one OB is load kVA, kW, OA is kW, and OB is kVA, and this one OD is equal to CD, that is CD leading kVAR supply by the synchronous motor, and OC is equal to, sorry, this OD is, that is the uh, OD is equal to CD leading kVAR supplied by the synchronous motor. How much amount of load it is supplying is act as a synchronous motor. Next, OC is equal to combined kVA, OC, this one combined kVA. Next, AC is equal to AC, that is combined load kVAR, that is AC. AC. So from this we can do the problems. Note down a first problem. This is on power factor improvement. A factory has a total load of 1800 kilowatts at a power factor of zero point 0.6 lagging. It is desired to improve the power factor to 0.95 lagging with installation of synchronous condenser. So, he given total load is 1800 kilowatts. What is the power factor? It is working at zero point 0.8 lagging. Now we have to improve this 0.6 lagging to 0.95 lagging. So what we have to do? We have to connect synchronous condenser in parallel with this one. So first, and we have to calculate what we have to calculate. We have to calculate kVA rating of the synchronous condenser. Next, total kVA of the factory. So first draw the vector diagram and write the given data. So what is the given data? So he given load kVA, that is 1800 kilowatts he given. So kW by pi. So that is 1800 by 0 0.6. So which is 3000 kVA. Next, from triangle AOB, this one, OAB, sorry, O, sorry, AOB, this one, big triangle, this is outermost, AOB, AOB, this is the triangle. So for this triangle, the power factor angle is 0 0.6. Next, A, O, C, this one, small one, AOC, again we calculate the angle, that is 0.95. Cos inverse of 0.95 is 18.19 degrees. So load kVAR is equal to AB. So that is nothing but a OB sine 53.13 degrees. So that is 300 into 0.8. That is 2400 kVAR. So combined, if you combine kVAR is equal to AC, that is OA into tan 18.95 degrees. That is 18 into 0.329. So what is the resultant kVA? 592 is the kVAR. So synchronous rating is equal to AB minus BC, that is equal to 2400 minus BC. So that is 1807.8 kVA. So total resultant kVA of the factory is equal to OC is equal square root of OA square plus AC square. So that is square root of 1800 square plus 5592 square. So that is equal to 1894.95 kVA. So this is the value here. So from this kVA required of the factory is reduced from 300 and kVA is 1894. So at the expansion of synchronous condenser of 1807.8 kVA, improved power factor will affect good souls. So improved power factor will affect good amount of saving in energy meter. So in factory the use of synchronous the use of induction motor and fluorescent is common, and therefore overall power factor of the factory is low. Then how we can improve? A synchronous motor is used in factory, serves two purposes. So what are the two purposes? One is drive the mechanical load, and next one is to improve the load power factor. To improve the load factor, improve the uh, low lagging power factor. So it drives the mechanical load and to correct low lagging power factor. So from this OP, where is OP? This one is load kVA and OA, load kilowatt, and AB, load kVAR. So OC is equal to OC, this one, OC is equal to BD. This is this one, which gives synchronous motor kVA and BE. So here this BE is equal to motor load in synchronous motor. So from this you can see ED is equal to EG is the leading kVAR supplied. OF is the combined load in kilowatt. OD is equal to combined load of kVA. FD is combined load of kVAR. Also combined from the figure, the power factor of the supply is improved from 0.5 to cos pi 1 to cos pi 2. So if you take the second problem, in the second problem what he given? He given a synchronous motor absorbs 40 kilowatts, is connected in parallel with a load of 300 kilowatts having power factor of 0.85 lagging. If the combined load has a power factor of 0.9 lagging, how much leading kVAR should be supplied by the synchronous motor, and what is the power factor of the motor? So in this case, what he given? He given a synchronous motor. What? How much it is observing? It is observing 40 kilowatts. Is connected with the load of 3000 kilowatts, having a power factor of 0.85 lakh. But if the combined power factor is improved to a power factor to a value of 0.9 lagging, so how much leading kVAR should be supplied to the synchronous motor, and what is the power factor of the motor? So in this case, first you write the given data. This is the vector diagram what we have. This is a vector diagram. No? In this vector diagram, KW rating of the load is 3000 and power factor is 0.85 and phase angle pi 1 is equal cos inverse of 0.85, that is equal 31.79 degrees. So kVAR rating is equal to kW into tan pi 1. So that is 300 into tan 31.79 degrees, which gives a value of 185.94 lagging 94, that is kVAR value. So if lagging kVAR is taken as negative, leading kVAR is taken as positive, and then the phasor diagram is like this. So kVA rating of the combined load is equal to kW of the load plus kW of the motor. Then it will gives kW of the combined, combined load, that is 40 and 300 plus 40, that is 340 kilowatts. Combined power factor is how much? That is 0.9 lagging, and its value is 25.84. kVAR rating of the combined is equal to kW into tan pi, that is 3825.84, that is 164.666 lagging. So synchronous, so kVAR supplied by the motor is equal to kVAR of the combined load minus kVAR of the load. So which gives a value of 21.28 kVAR. So kVAR rating of the motor is equal to under root WKW square plus kVAR square, which gives a value of 45.35 kVA. So then what is the power factor is equal to kW by kVA. So that is 40 by 45, which gives a value of 0.833 leading power factor. So if you see the third problem, so in this third problem, what he given? He given a 400 volts three phase system has a 500 kVA load at power factor of zero point 0.5 lagging. The synchronous motor supplies a load of 100 HP. And what is the efficiency? 0.87 is used to improve the overall power factor to 0.94 lagging. Calculate kVA rating of the synchronous motor, power factor of the synchronous motor. So in this problem, what he given data? He given a voltage of 400 volts, three phase, and it supplies a how much power of 500 kVA load at power factor of zero point 0.5 lag. So synchronous motor is supplying how much? 100 HP and efficiency is 0.87 and the overall power factor is improved to 0.94. So previously it is zero point 0.5. It improved from zero point 0.5 to 0.87. Sorry, this is power factor 0.5 to 0.94. It is improved. It is improved. So when it is improved, when we connected a synchronous motor in parallel with the bus bar. So we have to calculate kVA rating of the synchronous motor and power factor of the synchronous motor. So write the given data from this one. So he gives motor output how much 100 HP. So here it is showing the supply is there. It is connecting the load. So that is 500 kVA at zero point 0.8 power factor lag. For this one in parallel, we connected a synchronous motor. Synchronous motor. So HP to convert this into watts, we have to multiply with 746. So that gives a value of 46,600 watts. So what is the motor input? Motor input is equal to output by efficiency. Output it is here and efficiency given in the problem, that is 0.87, which gives a value of 85.75 kilowatts. So the kilowatt rating of the motor is 85.75. Note down this vector diagram, the diagram and the given data note down. So if you consider the load, what is the kVA rating of the load? That is 300. And what is the power factor? That is 0 0.5 before improvement. Okay, before connecting the synchronous motor in parallel. Load kVA is 300 and power factor is 0 0.5 lagging. And what is the phase angle? That is pi 1 is equal to cos inverse of 0 0.5, that is 60 degrees. So kW rating of the load is equal to kVA into cos pi 1. So that is 500 into 0 0.5, that is 250. So kVAR rating of the load is equal to kW into tan pi. So that is 250 into tan 60. So that is 433 kVAR rating of the load. So from this, what is the combined load? Combined load is equal to combined load is kW is equal to kW of the load plus kW of the synchronous motor. So we have to add these two, that is 250 plus 85. Then we get a combined kW, that is 3035.75 kilowatts. So what is the combined power factor it is improved? That is 0.9. From this we can calculate we can calculate the angle total power factor, that is cos inverse of 0 0.9, that is 25.84. So kVAR is equal to total kW into tan pi. So that is 335 into tan 25.84 degrees, that is 162.6 kVAR combined kVAR. Now deduct these two. So this is the vector diagram where it is showing this is the combined kW. Here up to here is 250 kW and the combined, this is the synchronous motor we added, that is 3035, and this is 270 and this is 162.6. So the synchronous motor kVAR supplied by the motor is equal to kVAR of the combined load minus kVAR of the load. So that is equal to 270.4 kVAR. Note on this, note on this vector diagram also. So this one is the synchronous motor and this one is the combined. So kVA rating is equal to square root of kW square plus kVAR square. So that is equal to 85 square plus 250 square, that is 283.67 kVA. So power factor of the motor is equal to kW by kVA, which gives a power factor of, that is 85.283, that is 0 0.3 leading. So this is the power factor of the synchronous motor, that is 0 0.3 leading. So what we discussed here is the problem shows that when a synchronous motor is connected in parallel with the plant, it improves the power factor. It improves the power factor. So synchronous motor is used to improve the power factor. And we done the problems on that one also. When we connect, we noticed before the synchronous motor is connected to the plant, what is the power factor? When we connect a synchronous motor in parallel with the plant, then how the power factor is improved, and what is the kVA rating of the synchronous motor, and what is the power rating of the synchronous motor. So if you see from examination point of view, so in examination he gives explain how a synchronous motor is used for power factor correction. So that means how a synchronous motor is used for power factor improvement. Note down this problem also. So in this problem, what he given, a synchronous motor observing 600 kilowatts is connected in parallel with a load of 240 kilowatts, having a power factor of 0.85 lagging. If the combined load should has a power factor of 0.8 lagging, how much leading kVAR should be supplied by the synchronous motor, and what is the power factor of the motor? This is similar to the last problem what we have done. Here he is asking the synchronous motor kVAR and power factor of the synchronous motor. So here if you see the power factor is, so here the asynchronous motor observes 600 kilowatts is connected in parallel with the load 240 kilowatts having power factor of 0.85 lagging. If the combined load should have a power factor of 0.8 lagging, how much leading kVAR should be supplied by the synchronous motor, and what is the, you do this problem for next class. If you have any doubt, ask me, I will explain this. Okay, thank you.